Last one. All right, so let's go in and take a look at one similar to number 36. I might change it a little bit. So 36 reads that a diffraction grating has 5,580 lines per centimeter. So this is that, that grading parameter. So this is 5,580 lines per centimeter. And we're going to need the spacing between adjacent slits. So what we're going to start off with is calculating the reciprocal to get the adjacent spacing. So D is 1 over 5,580, but then this will be in centimeters, and then we'll convert that into meters. So what's our value? What's 1 over 5,580 going to be? 1.79 10 to the minus 4. And then centi is, 10 to the minus 2. And so 10 to the minus 4 times 10 to the minus 2 is 10 to the minus 6 meters. That's our slit spacing. Okay. So the grating has 5,580 lines per centimeter. When a beam of monochromatic light goes through it, the second pair of bright spots occur at plus and minus, this is where those negatives come in, above and below, 26.3 centimeters from the central spot on the screen, which is 42.5 centimeters past the grating. So we got our grating. I'm not drawing 5,580 slits. We'll draw a bunch. And we're going to have our little screen here. Now we figured out that our spacing between the adjacent slits is D. From the slits to the screen was 42.5 centimeters. And then they asked for what is the wavelength of the light. And they ask for how far apart of the screens for the next pair of bright spots. So the second pair occurs at plus and minus 26.3 centimeters. So let me draw in my little picture. Okay. So this is the intensity versus these are, plus Y and minus Y kind of positions. And so we have the central maximum here and then a bunch of nothing. First order here, bunch of nothing. Second order here, bunch of nothing. Third order there. First order, second order, third order, like this. And so what they give us is this distance to this second pair. So we get Y2 is, in this case, plus 26.3. And this will be minus 26.3. Okay. And they're symmetric, so we don't really need to worry about the negative one. We'll just work on this positive one. Notice that this is our central maximum. First order, max or bright. Second order, max or bright. Third order max. Yeah, sure. I hope. And then the numbers are nice. This is the 0. So our formula is the d sine theta is m lambda. And m's are all the standard things, 0, plus 1, plus 2, plus 3, minus 1, negative 2, negative 3. So like so. So first thing they want, what's our wavelength? Okay. And so since we know the y and we know the r, we can get the theta because we have that same, you know, tangent of theta is y over r. So we can get the theta, take the inverse tangent on both sides. Now, in this instance, these angles are not small. So you can't use the small angle approximation here. So for my theta 2, this is that inverse tangent of the y2 over r. They're both in centimeters, so I'll leave them. So this is the tangent inverse of 26.3 over 42.5. And so then our theta 2 ends up how much? Centimeters and centimeters cancel. Thank you. 31.75 degrees. Definitely not a small angle now. Okay. And that's usually how it goes. But what we're going to do is the same thing we did on all the problems. They're all going to solve the same. So it's kind of a nice thing, I think. Now we want the wavelength, so we're going to get it out of this formula. We got the theta, we know the d, and we know the m number from the picture. And so we can get the lambda. Okay. So the d value was our 1.79 10 to the minus 6 meters. Sine of our angle, that is not small, 31.75 degrees. Over the order number, and we're doing the second order max, the second pair of brights. So that's going to be our, plus 2. And so what wavelength are we working with here? Again, very similar to what we're going to do in the lab is we're going to measure things to determine the wavelength. And you'll have to do this reciprocal because they'll give you the line density. And you'll have to get the spacings. And I think it's the 300 is the one they do. I think we have a 100 lines per centimeter, a 300 lines per centimeter, and a 600 lines per centimeter were available. Sweet, 471. And Maxwell already converted it for y'all into nano. So it's going to look like 4.71 10 to the minus 7, and then when we convert, it'll be 471 nano, just like we talked about. All right, so now we have the wavelength. And so then what they ask for is what are the spacings for the next pair, okay? And so we can go in and work on that. So then this will be theta 3, and this will be our, y3. So that's what we're after. So now we're going to run it backwards. So now we know the wavelength and we know the spacings. We can get the angle. And with the angle, we can put it into the geometry and get the y. Okay. So this one was part A. And then what we'll do is we'll start off with this one. So we're going to start off with our, and this will be theta 3 is m lambda. And we want to solve for this angle. So we'll divide both sides by d. And then in order to get the angle, we will then take the inverse sine on both sides. So our theta 3 angle is that inverse sine of, and the order number for the third pair is +3. So that's very nice. 3. Our wavelength is our 4.71 times 10 to the -7, or 471 nano. And our spacing is that 1.79 10 to the -6. This will give us our next angle. So now since the theta 2 was 31.75, then the theta 3 will be bigger. Again, definitely not small. $52.13, thank you. And then we find our y value. So the R was 42.5 centimeters. I'll leave it that way. Tangent of the angle we just found, 52.13 degrees. And so then this will give us the y value here, and then we'll make it negative to do the y value down there. $54.65. So that's the up one. And then the down one is the same thing, but minus. So this is B with the little plus and minus. Okay. Now, that was the question they asked. I want to do one more thing. Okay. So let me say we'll make question C. And we're going to ask how many? Right. Spots, lines, fringes, how many maxima are on the screen? Okay. So the thing is that you can keep going further and further out, and really the point where you no longer hit the screen is when this angle from the center out is 90. So at theta equals 90, we're no longer hitting the screen. So anything less than that should form on the screen. So what we're going to do is we will go in, we will take theta to be 90 degrees and figure out what the m is for that angle theta. Okay, so we're going to go in and write down our d sine theta equals m lambda. We're going to solve for m, and we're going to load theta in as 90. So we'll divide both sides by the wavelength. Flip the equation. The d value is our 1.79 times 10 to the -6 sine of 90 degrees divided by lambda, which we found to be this 4.71 times 10 to the -7. And then what we get is that, well, the sine of 90 is just +1. Okay. And so as a decimal, what does m turn out to be? And then we're going to talk about this just briefly. 3.80. Thank you. Okay, now m should be an integer, right? That was our deal. The m was 0, plus or minus 1, plus or minus 2, plus or minus 3. And the thing is that with this answer, you would go, well, maybe it's 4, but that means you went up on the m, which implies you go up on the angle beyond 90. That's not okay. And so while it looks like it should round to 4, it actually can't, because you can't go higher. This is the absolute, this is no longer on the screen at 90 degrees. So then what you have to do is truncate this. And so then the maximum value for m is 3. Well, if our maximum order number is 3, then how many bright lines, spot, fringes, maxima are on the screen for this grating? Beautiful. We drew it. It's 3 here, 3 there, and the center. So the answer for how many is that this will be 2m plus 1. So twice the 3 plus the center one, above and below, and then the center. So yes, it is indeed 7, just like Peyton said. Questions? Yeah, so the maximum order would be 3, so up to 3rd order, but the number of actual spots or lines or whatever is going to be 7. So it depends on what they ask. If they ask for what's the maximum order, then it's 3. 3rd order. Can the question be asked for the single slit where we only deal with the dark? Yeah, actually, you could do the same technique with the single, but I think you're in many cases going to get a whole bunch. But yeah, you can run the single the same way, kind of things. And then once you know what the orders are, we'd have to figure out whether they wanted, if they wanted the darks, then it's twice the order number for the darks. And then it's whether we made it to the next max. And I guess if you round down, then you didn't make it. I don't know. That might be a little complicated. But you kind of do the same kind of thing. But yeah, but it might be a little complicated. All right, y'all. We made it. So hopefully you see how similar the problems are to one another. That they're, in my mind, they're all kind of the same problem-ish. There's little differences that you got to be a little careful with. The single is only the darks. The double does darks and brights, but the darks are messed up on the order numbers. And then the grading, you usually have to worry about that parameter. And on the grading, there absolutely is no small angles. But I didn't do any small angles. So I always did them all the same. Okay.